Okay, this video is about the line integral of a scalar field. So for the line integral, we talk about a given line we represented by s. So here's a 2D example of the line, which is represented by xt and yt, and starting from t2 to t0 and tf. And we're also talking about a scalar field represented by fxy, which means for any xy we have defined some scalar value associated with that point. So right hand side we show a picture of the setup. So we're given a line is S is represented by its parametric form xtyt. So this blue line represents the starting point and ending point. And for each point as a line, we define a scalar f of xy. So this one can be considered as, for example, the height associated with every point. So the line integral is denoted by integration of fxy over d of s from t is t0 to t is tf. So essentially we can consider this as integration to find out the area of the surface. The area of the surface, let me represent it by the red area. So it's the area of the surface. Okay, because this is a curve of the surface, so it's not easy to compute it by using the scalar integrations. Okay, so the key idea for the computation of the line integral over a scalar field is to convert from the original one, because we don't know how to compute this integration because of ds. The idea is we want to try to rewrite the original integration. This is mathematical integration about how to compute the area of surface. We convert that into integration over the parameter d of t. So because this is only one scalar, so it's just a scalar integration, and we can compute it. And if we can figure out this specific form, then we can compute the line integral very easily. Now, for the first part, we just have to replace fxy, in which replace x by xt and y by yt, which is straightforward because we're just talking about the point on the curve. So we can replace other point we don't care, so we just have to replace x by its xt, okay, and y by its yt, and this is xt, this is yt. So it's a function of t. We replace this f by a function of xy as a function of t. So which is done. The next part we're trying to rewrite a ds. This is very confusing, very challenging part. We hope to write a ds into something times d of dt. Okay, now we explain how we rewrite ds into something times dt. Okay, so let's take a look at the physical meaning of d of s. So d of s is just a very small tiny piece. If I can copy, this is a copy of the original line, and ds is a tiny piece of the segment on the s, which is represented by over here. This is d of s. So the essential d of s talks about. So if you write this form, the d of s, so d of s can be written as ds over dt times dt. Okay, so the ds of dt is the rate of change of ds, right? The rate of change, and you times the little d of dt, right? Okay, now what is the ds of dt? The ds dt, if you take a look at this ds dt, so ds dt is the small change of s over a very tiny bit of dt. Okay, because if I can project the ds, because the ds is a curve, if I project along the axis and the y-axis, well, this is just the square root of dx squared plus dy squared, which is just ds. Okay, what this means is if we change a small tiny of t from t to t plus dt for all t, all the possibility here, what happens, we do the small change, what happens, it will change d from original x plus dx. Original x, which is the x associated with t. We also change the y from y plus dy. Now, how is dx dy related to dt, which is apparently defined by this function over here, right? That's why this is just the change of ds is a length, right? Which is just dx squared plus dy squared. Okay, so that's why here comes to the ds over dt becomes square root of dx squared plus dy squared. We just replace here by this. So this is a very good approximation. If dt is very small, consider dt is very small, so this straight line is a good approximation of the little bit curve over here. It's a good approximation of that. So after we do that, we can replace ds by square root of dx squared plus dy squared. Take a square root of that and over dt, and we can move the dt inside, which is just square root of dx over dt squared plus dy over dt squared. Because we move dt inside, we have to put a dt squared, and we just put a divide by each one, so we have this form. So essentially we have this form. So this will be the form t is t0, t is tf, f x t, y of t, time the ds of dt is just given by this. Okay, let's move this, times square root of x dot t squared, that's the dx over dt, plus y dot t squared times dt. Okay, that's the way how we compute. We can convert the original integration over line by integration just by a scalar. Okay, by a scalar integration, which is we know how to compute this. So here's a simple example talking about how we compute the line integral. So assume that I have the line represented by t squared and 2t squared by letting t move from t to 0 to t to 1. So they will define a curve, our line. And this vector field, a scalar field defined by fxy with a y minus 2x. Okay, with any xy point we can find a scalar associated with that. Okay, let's use what I mentioned before to compute the line integral. Okay, this is t0 to t1, so you never change the integration lower bound, upper bound. What you change is just change the fxy. As I mentioned before, fx here is just y minus 2x. Okay, so here this first one, you consider this first one is just by xt, and this is yt. This is by definition rt is xt yt. So we have to replace this one by y of t, and replace this one by x of t, and again we have to replace ds by square root of x dot t squared plus y dot t squared and time dt. Okay, now we are done. Okay, replace this t from 0 again. I drop the t, just 0 to 1. And y is, here is yt, replaced by yt is 2t squared plus 1 minus 2xt, 2xt is 2t squared. This is square root of x dot t, x is here, xt t squared. T squared derivative is 2t squared plus y dot, y is 2t squared plus 1, so its derivative is 4t squared and time dt. Okay, this just cancels out to be just 1, so it becomes simple. So 0 to 1, the one that drops a 1, so this is square root of 2t squared is just 4t squared plus 4t, the whole part squared, it becomes 16t squared d sub t, which is just 0 to 1, so this is square root of 20 times t squared. Okay, so let's move the t outside, so it's just square root of 20 times t d sub t, which is 1/2 is square root of 20 over 2 times 1/2 t squared from 0 to 1. Okay, so this is just square root of 20 is just 2 over square root over 5. Okay, so this is 2 will be cancelled out, so this will be just cancelled out. So it's just square root of 5 times t squared, evaluate 0, 1, which is square root of 5 times 1 squared, which is 1, and minus 0 is still 1, right? So the square root of 5 times 1, of course I can drop it, just square root of 5. So okay, I hope this will give you a good example about how we compute the line integral. And there's a reason, the key idea is what's the main reason why we can write ds over dt. Ds by, okay, I can rewrite ds by this form because ds over dt is this, so ds will be just equal to dx dt squared plus dy dt squared, because it just moved the dt to the right hand side of the dt. That's why it's become, why I can do this way. Okay,